Hello everybody and welcome back to another video. Today we're going to be looking at the 6th video in the HackTheBox Introduction to Binary Exploitation series. This video is really going to ramp up things. We're going to see a lot of new stuff and cover a lot of things that we've seen before. So as always, if you're interested in things that we have seen before and you want to recap and rewatch that, or you don't understand something here, go watch the rest of this series, because gradually we'll be covering more and more difficult topics in binary exploitation. So watch these first and let's get on with the video. So the first thing we are going to be doing is we're going to be playing with the binary, running it and checking the security that is set on the binary. So let's do just that. So the first thing, we have this binary PwnShop. We can do file on it and we'll see that it is an ELF 46-bit executable. It's least significant bit, and it has been stripped, which means that all the symbols, so function names and stuff, have been taken out. Then we can do checksec PwnShop to see the security bits that are enabled on this binary, and we can, for example, see that NX has been enabled. I've covered NX in the past, but pretty much it means that the stack won't be executable. So we cannot just find a buffer overflow, get shellcode in the stack and jump to that, because that won't execute. So that pretty much means that we need to do return-oriented programming, or ROP. Next up we have pi, and pi means that the binary is position independent. So usually if pi is disabled, the binary will be in the same location in memory every time you run it. However, with pi that is not the case. Now why is that difficult? What does that change for us? Well, obviously, when we're doing ROP, return-oriented programming, we are going to be using gadgets. And those gadgets are pieces of shellcode in the binary itself. Gadgets that we need to use to construct a chain so that we can actually get something done. So we need to jump to those, and those are in the binary itself. And we need to jump to an address. And usually the address is static, and we can just jump to it. However, with pi enabled, that's not possible, because the address will be different every time you run it. So it will be impossible to know where to jump to, unless you can find a way to leak an address in the binary, and that way calculate an offset and get around that. And that's what we are going to have to do in this video, well, because pi is enabled in this case. So alright, I've talked a lot about the binary, let's actually run it. So if we run it, we see, okay, we can buy, sell, or exit. So let's buy. Sorry, we aren't selling right now, but you can place a request. So I can place a request, and we go back to the menu. Now we can sell. I wish to sell fish for $1. It says 1, the best I can do is 13.37, and we get the prompt again. And that really is the functionality of this program, so there's not really that much to it. Now let's jump into Ghidra and see what we can find here. So as I said, the binary is stripped, so we won't have function names, but I've renamed them in Ghidra here, so the buy and the sell function. So first let's look at the sell function here. The sell function is going to ask us what we want to sell. We are going to read 31 into the stack that only holds 8 bytes, so we have a buffer overflow here. Good to keep in mind. Okay. Then it says how much you want to pay for it, and we read 8 bytes into local 28. If those 8 bytes were equal to 13.37, then we're going to output sounds good, leave details here, and we are going to read 64 bytes into local 20, and local 20 has been set here to point to this place in memory. Okay, and then lastly, if that wasn't equal, so if we didn't enter the right amount, it's going to print out what we said, and then the actual number that it wanted. And we can see that from running it here, we saw that it printed out what? 1 question mark. The best I can do is 13.37. Now there's an interesting thing to note here. Do you notice how here there is a new line after this one? And in the code there isn't a new line. It's just our input. So that kind of begs the question, why is that new line there? What is it doing there? It was part of our input, but why? And is that always the case? Let's see. If we try to sell for this amount, we also see that new line. However, why? That doesn't make any sense, does it? What if we do something like we sell again, and this time we try to fill everything we can, so we could fill it with 8 characters. And now it says, what are 8 characters and then some unknown characters or some bytes that doesn't know, that we didn't even enter. Like this stuff, we never entered that. What is it? Where does it come from? So very peculiar behavior here. But we can analyze that. So if we look at the code here, we read with the read command function. The read function is not null terminated, or what we read is not null terminated. So we just read it in exactly as we get it. It doesn't add a null to the end. Then in the printf, where we print that out, we use this %s. And if you look at Wikipedia here, we see %s prints a null terminated string. What is a null terminated string? Well, it's in memory. You have a string, so a range of bytes, followed by a null. So what this %s will do is it will take this pointer here, or like this location, we'll go to there and we'll say, okay, I want to print out all of the bytes until I meet in a null. So a 0, 0. However, because read doesn't add in null to the end, we input our 8 bytes, or 8 full bytes, and that's it. Those go directly into memory. And then what follows there, well, it's just going to follow directly without a null in between. So that's why what follows after our input is also printed out, and those are these weird characters that we see here. Like, these can't even be printed. And we'll see also if we run this again. So we get different characters than the first time. This time we only got 1 character, which is also peculiar. If we try to sell again, so we get the same 1 character again. If we exit the program and run it again, and now we try to sell. Oh, wrong place. We see that we get different characters. And if we sell again, oh, wait, I wanted to sell. Okay, let's do it again. I want to sell something for 1, 2, 3, 4, 5, 6, 7, 8, and we see we get those same different characters that we got in this runtime. So we're printing some address that changes every time we run the program, but that stays the same every time we loop within the program. So that should tell us something. And if you've worked with or listened closely to what I told you about position independence, so pi, then you might notice, hey, maybe this is some address that has to do with the binary, that has to do with something within the binary. Could that be the case? And well, if we look at the code here, at the top, this is all of these parameters or variables will be on the stack. The stack starts here with this var1, goes down, goes down, goes down, and here is our place where we input then. And this local 20 follows directly below it. And this local 20 is a pointer. And what is that pointing to in the runtime? Well, it's pointing to this place here in our binary. So this 40CO is a place in our binary, and that's where local 20 is pointing to, and that is the address that we are leaking. So we have a leak in our binary. So okay, we've just identified that we can leak an address from the binary. How can we use that? What can we do with that? Well, if we know that one address, and that address we've identified in Ghidra is right here. What we can do is we can take what we have, and so first of all, we want to offset between this here, so this theoretical address that we're leaking, and the beginning of the binary. So the beginning of the binary is here at 0000, and our address is at 40CO, so 40CO. So what we want to do is we leak this address, the actual address in the binary. If we then remove 40CO from that leaked address, then we get the beginning of the binary in our current runtime, in our current run of the application, because every time we run the program, the binary is going to be in a different position. But then we know the beginning of it, and from that beginning, we can jump to any place in the binary. For example, if we want to jump to this test, we just have to add 11AB, the address that we see in Ghidra, to that beginning address that we leaked, or that we were able to calculate through the leak. And this is something that for any ROP chain we want to create, we are going to need. So let's put that in a script and let's see how that works. So, all right, here we have the script. So the first step is to leak the binary address, because we are going to obviously need that. So, okay, we open the process, we send the line that we want to sell something. What do we wish to sell? We don't input anything because that doesn't matter. Then we have our leak padding, and this is just 8 random characters. Yes, because the read was not null terminated, so just 8 random characters will work. So we input 8 ones here, and we send that for how much do you want for it. Then we are going to have to receive a line. And let's see what that line is that we are going to receive. So we are going to receive this line, and we want to cut this part out. So after our input and between the question mark and this part that's currently question marks, because my terminal does not know how to show it, because it's, well, it is an address, so it's going to be bytes that don't represent characters. Okay, so in our code, we receive a line, we split it on those 8 ones, that is our input, so I can actually change that to leak padding, that would be better. Take that first part and we split it on the question mark, so what we are left with is only these bytes that we want. We then turn that into a byte array, and we do an LJust, and what LJust is going to do, it's going to add these null bytes to the left side of our input, and that's just so, obviously we're working with a 64-bit, so addresses are 8 bytes long, so this just ensures that what we get is 8 bytes long, and then we unpack that with endian is little, because we saw when we did file that it was a LSB, so least significant bit, so the endian should be little when we unpack it. And now this is where we remove this 40CO, this 40CO, and that is to get the position of the beginning of the binary in memory, because now what we have at this point is the position of that random place in the memory of the binary, that location there. But now we want to know the beginning of the binary so that we can easily calculate positions within the binary later. So that's what we're doing here by removing this 40CO from that offset, and then we just print out, we log, right? We leak the binary address, and we log that. So let's see if that actually works. So if I do a run that script, we see, okay, we leak an address here, and that seems to be quite alright. Now something to notice here, this binary is an LSB, so if we want to read this better as humans, we should read it from per byte from right to left, which is really confusing because in memory it will be at address 0080B586CA55. It's kind of confusing to read, but that's just because it's least significant bit. So now we were actually able to leak an address. Beautiful. Now let's see what else we can do with this binary, because now that we leaked an address, all we need to find is a buffer overflow that allows us to override a return statement. And once we have that, we can start creating a return-oriented programming chain. So a gadget chain that's going to allow us to get a shell, hopefully. So let's continue looking into our binary, and we're going to continue with the by function, which is a very easy one. So we have a stack that is 72 bytes in size. We read in 80 bytes into that stack of 72. So we have a buffer overflow of 8 bytes, and then right after we return. And in this case, that will probably mean that we overwrite the return address so that we get a segmentation fault. So let's see if we can trigger that segmentation fault. So we're gonna quickly grab 80 A's here. Okay. Then we are going to run the binary. We want to buy something, enter our 80 A's, and we see we get an segmentation fault as expected, which is great because we need the segmentation fault in order to, because that segmentation fault means that we try to jump to an address that wasn't executable code. So that means that our input was used as the instruction pointer, was set to the instruction pointer, and that didn't work. So we control the instruction pointer, and when you control the instruction pointer, you can obviously start jumping to places and get a ROP chain going to execute code. So great, we know that we can overflow a buffer. So we had just identified this buffer overflow where we control the instruction pointer afterwards. But we see an issue with that. We have a buffer of 72 bytes and we write 80 bytes in there. So we only overflow 8 bytes, which means that for our ROP chain it can only be 1 link long. We cannot use more. So we need to find in the binary a gadget that's going to do everything for us just at once. It's going to give us a shell or read the flag at once, which there is not. Or we can do another thing, and that's called a stack pivot. What is a stack pivot? The idea is that we have this stack. We control a portion of it. And what we want to do is we want to move the stack pointer back to a place that we controlled earlier. So for example, we have this one call that we can make. We have these 8 bytes that we can overwrite. We're going to jump back to the program. In the program, we are going to say, hey, move the stack pointer up by a bit so that it goes back to a place that we control. And that way we have more space to work with. So let's try that in Paint. So we have the program up here. We have the stack is this part, and this is that buffer that we control. We control this, and this last part is where we overwrite the instruction pointer. Is that last part? We don't control the part after that. So what's going to happen? Our instruction is going to be executed. We're going to use a gadget from the program. So we're going to jump back into the program at some place. It's going to do something, and it's then going to return. When it returns, it will return automatically back below our instruction pointer, because the stack pointer, because that's what would happen. Because we pop the next value into the instruction pointer. However, RBP is here. What if in here we subtract from our BP and then we return? In that case, we would subtract RBP, so RBP would move upwards to there, and we control this, right? And then when we return, we would jump back to RBP instead of below the place that we controlled. So that means that we control this. Currently it contains A's, but we can put our ROP chain in there and get more place that way. So that's the idea behind like this stack pivot that we're going to implement here. First of all, we need to find that gadget that's going to allow us to modify RBP and return afterwards, so that we can actually do that. So let's try to get that to happen. So how are we going to find gadgets? Well, let's use ROP gadget. For that, --binary for to specify the binary PwnShop, and then we'll do --only, and I only want to find gadgets that have sub and return. Let's see. Okay, so we have we have subtract RSP, and I am very sorry. In this drawing, RBP should have been RSP all along because obviously it's a stack pointer. I don't know how I got RBB in my head, but okay. So RSP is what we want to be moving upwards so that we have more space to work with. And we find this gadget here that's going to move it upwards by 28 bytes. So RBP is at the bottom here, and we move it. If we move it up by 8 bytes, then we're back at where we started at our original return address. And then we move 20 bytes more upwards. So that means that we have 20 bytes to work with in a ROP chain. 20 divided by 8 is 4, so we have 4 links that our chain can have after we implement this. So let's try to implement this and see if we can actually use that. So before we put that in code, quickly let's look at how our actually buffer that we are going to overflow is going to look. So imagine this thing on the right here is our buffer. We have our address that we control, our first return here. This is obviously going to jump to our sub RSP that we found, which is then going to subtract from RSP and jump somewhere back up here. So this is somewhere that we control, and this is actually going to be our ROP chain. Now, we need padding up here, and we can calculate what that is, because this whole part is 80, this whole buffer is 80 long, and we subtract 20 hexadecimal 28 from RSP, which is 40. So that means that we jump back to here in the middle, so it's right in the middle. So that means this padding is going to be 40 bytes. Now after a ROP chain has a maximum length of 4 operations, so 32. After it may be the case that we need more padding. For example, if our ROP chain is only 2 operations long or 1 operation, that we need some more padding, and that's something that we need to calculate depending on how long the ROP chain is. So let's do all of that in code. So first of all, we have the padding to the ROP chain, just 40. Then I specified the cell function here. Now, obviously, the cell function, this first value, I just got from Ghidra. So just the cell function has that address, 126A. And then we need to add the binary offset to it, because obviously we're working with pi here, so it's position independent. But luckily earlier we calculated this offset, the start of the binary in this actual instance of the binary. So that's the start of the binary in memory. So if you just add this offset to it, then that will be perfect, and we will have the location of the cell function. Then we can start our ROP chain. And our ROP chain, in this case, I just want to call the cell function twice. Just see, does everything work? Can I now have a ROP chain that's longer than just 1? Then we need to do the padding to the stack pivot. So this is the padding below our ROP chain, between a ROP chain and like the actual stack pivot that we're doing. And for that, we're going to take the whole buffer. We're going to remove the first padding, remove the length of the ROP chain, and that's what we have left. So that's going to be, in this case, 16. So 16 Bs in this case. Then we can construct a payload. So first we have the padding to the ROP chain, then we have the actual ROP chain, then the padding to the stack pivot, and then we have the sub RSP, where in the same way as with the cell function, I calculated the address by using the value that we got from ROP gadget and adding the binary offset to that. So then we have a payload. I'm going to print the payload and I'm going to send it. And then we're going to go into interactive so that we can actually see if we call the cell function twice now. Okay, so let's run this. We see our payload here contains these A's and then contains 16 B's here as well, so it's what we calculated. And it calls the cell function, so I can sell something now, and it calls the cell function again. So that's great. We've just created or gave ourselves more space to work with to actually create a longer ROP chain, and which will be needed in the next part where we try to exploit that. We have place to work with to start building a ROP chain. However, we don't have any gadgets in this binary. There's not enough gadgets to actually get something going. That's an issue, And in order to do that, to fix that, to actually get a reverse shell here, we need to use a technique called Ret2LIBC, so Ret2LIBC. Now what does it mean? So return to obviously stands for the returning that we do in a ROP chain. We always return to a different position. And we're going to jump to LIBC. What is LIBC? Well, a binary obviously runs, and it's going to use things that every binary uses, like puts or gets or printf, stuff like that. And those are obviously not stored in the binary itself, but they're in a library, and that's LIBC. Now LIBC is somewhere in the binary running. So somewhere in the memory it's running, and we don't know the location of it because it's going to be different every time. And that is an issue because obviously we need to know the location of it. And once we know where the location of libc is in memory, we can then calculate where system is in libc, and we can then calculate where the string /bin /sh is in memory. And that way we can then construct a ROP chain that is going to get us a reverse shell. But first of all, we need to be able to find out where libc is. And to do that, we need to leak an address. Now, how are we going to do that? So first of all, we currently have the ability to create a ROP chain, and that's going to execute stuff. And one of the things we can execute is a puts, so we can output something. We want to give that an argument, something that it's going to output. What if we output that the pointer to where libc is? That way we can then obviously leak the location of libc. So that's what we want to do. So let's do that. So first of all, in a Ghidra here, I went to the .got, so the global offset table, .plt, the procedure linkage table, yeah. And here we find puts, for example. So what is this? This is going to be when we run the binary, because currently we don't know it. When we run the binary, this is going to be a pointer to where puts is in libc, in memory for libc. So this is the address, so 4018. So that is what we want to output, that pointer, because once we know that pointer, then we have enough information to calculate all the rest. Now we also need to find the puts in the binary itself, and we can just follow this to the PLT table here, and we can see, okay, at this address, it's going to jump to puts, so it's going to execute that. So perfectly, we have those two addresses. So okay. I put them in here, so we have the puts that we saw first, that is the link to memory, pointer to memory, and then we have the puts that's going to be executed. We then also need a pop RDI, because obviously we need to pop that first argument to execute, we need to pop that. And lastly, after we've done all that, we want to continue running the binary. We don't just want to crash, because this is not going to exploit anything, we need to keep going. So that's why I also put the by function in here. And this by function is going to allow us to afterwards run through the binary again, so that we can exploit it again, but we now obviously have this information. We then also have the padding. The padding is the same because we still obviously need to use that stack pivot. That allows us to get some more space to work with. So that's the only thing that's really changed here. So our ROP chain now is we're going to pop RDI. We're going to then pop the puts address, the puts pointer, as an argument into the local puts function that we're going to call. Obviously, that's eventually also going to call the libc one, but yeah, we're just going to output that pointer so that we have an address that's running, and afterwards we're going to return to the by function, so that we can keep going. We then have the other calculations that we went over earlier for the stack pivot, but that's now we've solved that. We know about that, so just know that that's going to have to happen, but we don't need to worry about it anymore because we understand how that works now. So let's actually try running this and see what happens. So now if we run the binary, we will notice that we leak the binary offset that we had earlier. We then leak puts, the libc place of puts, so that's this address. You can see it's a very high address, so it's somewhere at the end there where libc is normally. So if it's a high address, then you know, okay, that's probably right. And then we switch to interactive mode, and then we see we get into the cell function or the by function. Yeah, the by function. Again, so we are still in the binary and we can still do stuff, but we have this new information of where puts is. And that's great, because what will we do now? Well, we will use this binary again to trigger another buffer overflow, because Here there is a buffer overflow when we enter the details. And this time we can actually start doing some exploiting. Let's try to get an exploit working. What do we need for the exploit? We need the system, the location of system, and we need the location of bin.sh, because we want to pop bin.sh and use that as an argument to system. We need to use that from libc, and we now know a single address in libc. First things first, let's leak the libc address. Let's leak the beginning of libc, so we have an offset that we can work with, that we can count stuff with. Okay. First of all, what is the libc that we are locally using? Well, we can use LDD PwnShop. We can see, okay, we're using this libc, which is at this location. Perfect. So now we want to find, well, puts, when we were running the binary, puts was here. Where is puts normally? When the beginning is 0, 0 and the offset is 0, where is that? So to do that, we can use Ret2LIBC, and we're going to supply Ret2LIBC with -s, supply our libc here, and we're then going to grab for puts. Okay, so we want to find puts at libc here, so this one, and this is at address 765FO. Okay. Now we know that. So now we know that, well, our binary, we leak this address. So if we subtract this local one, this normal one, from that, we know where the beginning of libc is in our binary, and that way we can use the same method to calculate where the further system and bin.sh will be. So let's do that. So up here, we're gonna uncomment step 3 here, which is finding the offset. Okay, so finding the offset, we have our libc puts here that we just found through that command. And now we will also want to find the local place of system. We can do that in the same way, just grab for system. Okay, we have that address. And then we also want to find the string, a pointer to the string, or the string /bin/sh, so we have a pointer to that we can pop. So let's do that. For that we can just use strings. I'm going to do -a and -t to ensure that we -tx to ensure that we see the addresses next to it, and then we're going to supply this library again. Okay, and then we obviously have to grab for /bin/sh. And here we see, we can find that at this address here. So we put all of those in to our script. And now we can calculate the offset. So like I told earlier, we take the leaked puts that we had, and we subtract the normal version from it, so that we have the beginning of libc in memory. Then we have that beginning, and then we just add up the system one we had, and that's where the actual system is going to be in this case. So as you can see, system is our offset plus where we found system locally. We can also do it for sh, and then we have those offsets, and I also printed them out. So if we run this binary again, or if we run our solve script again, we can see, okay, we calculated the system location and the sh location in memory. Great. Can we now finally get a payload working? Well, yes, we can. So let's finally do step 4, exploit this. So our ROP chain this time, like I told earlier, is going to be a pop RDI. We're going to pop this sh string into as the not argument, so that's going to be the one argument to system. System is then going to be executed. We obviously still have that stack pivot that's working, so we still have to include the stack pivot so that we have the space to actually do that. And then we just send the payload. And then we go into interactive so we can use that. So let's see if that works. If I do ID, we can see, yes, we have code execution, we have a shell here. So that's perfect, great. We have a local version working. But what will happen when we try it on the remote, on the server? Because a local exploit is nice, but I already had root, so I didn't really do anything. I want to exploit the server where the flag resides. So let's change our script so that instead of making a local process, we will call this remote server at the following port and see what happens. So if we run our script again, we will see we still leak this address, all these addresses, but we did not get a shell, we get an end of file instead. So something went wrong. And what went wrong? Well, the server might be using a different libc, and in that different libc, like sure, we leaked the location of libc, but system might be at a different location, at a different offset. SH might be at a different offset, so therefore there might be an issue. Now, how do we fix this? How can we get the actual libc that's used? Well, we can't really like specifically know, okay, it's that one. We can get some options though, because libc is randomly somewhere in memory. However, this randomization only happens at the higher level bytes, not at the last bytes. So what does that mean? Well, for example, we leaked this address. This 6A0 is always going to be the same. The rest might change. As you can see, the other ones changed. So, but the 6A0 is always going to be the same. And that is because this randomization doesn't really work at the least important bytes. But we can use that because if we run it locally, we will see that it was different than 6A0. See, here we had 5F0, and running this will always be 5F0. So now all we really need to do is need to get a list of all the possible libcs that exist and see, well, for which ones is the puts offset going to be that 6A0, and then we know the location of everything. Well, that's obviously easier said than done, but luckily we don't have to do that. People have already made that database that we can query, and for example, libc.bluecat.me is a great website where we can try that. So for our query, we say, okay, we found puts at 6A0. We press find, and what are the possible matches? Well, these are all the libcs where puts is at 6A0. And now all we have to do is try out all of these. Luckily, there's only 3, so not a lot to try out. So let's start with the last one. If we click this, we can also see it already gives us all of these nice offsets like binsh and system. So okay, system is there, binsh is there. We can just put that in our script. So this was when we exploited locally, not important anymore. And now here we have the remote ones that I just pulled from the website. But you could also find these by downloading the libc and then doing the commands that we did earlier on them and find that. So that's really all we have to change, because these are the only things that have changed. And now we can check out if our binary, if we run it, it works. And we get an interesting error here. We get a argument out of range error. And I'm going to get into that in a second. But first I'm going to show you that this actually works. If we call it again, we see, yes, we get root, and we can actually get the flag and get the flag that way. So challenge solved. Great, great, great. But why did it fail this one time? Why was the leaked binary offset minus 4000? That doesn't make sense. Why is that the case? Well, if you noticed earlier when I was talking about leaking that thing, we had this gets, and gets was going to read 8 bytes, but gets was not going to append a 0 byte to the end of that. Then we were printing that result out in a printf. That printf was going to print until it saw is a null byte. Now, what might have happened here? That what we were printing out actually contained a null byte. So the address that we were leaking actually contained a null byte. So printf didn't print it all out, and we had no way of knowing it. So the program in this case crashed, but there's no real way to recover from it, because we don't know the full address. So that is going to happen occasionally. You could write some logic that's not going to crash, but it's just going to tell you that's happening. But it happens very occasionally, not always. So it's just when it crashes, know that might be the reason. So think about that. Why did this crash? Well, it's because there was a null byte where the program didn't expect it, because it's impossible to exploit when there's a null byte there. Or at least that's what I know of it. So that doesn't really matter. We still have a script that works almost all the time, which is great. We can export this binary. This was a particularly hard binary for me, I think, as well. So maybe rewatch the video, go and try it yourself. Make sure that you really understand what's going on and that you can get all of these concepts in your head. If you have any questions, as always, leave them down below in the comments. Anything that you want me to cover, let me know, because in the next videos I want to keep on covering things, and if there was something that I didn't explain well enough, let me know what it was so I can obviously improve. So that was it for this video. I hope you enjoyed it, and I hope to see you back for another one. If you liked it, like. If you want to subscribe. I make lots of these videos, so take care and goodbye.